And problem number 2 is 2936. I have a copper wire. I have a known resistivity. I have a certain area which I know. I don't know what you want to call that area, whether you want to call it pi r squared. It's an area. And it is 4.0 square millimeters. Let's give it a radius r0. And there is a current in the beginning going through, which is constant, conduction current, uniformly distributed over the surface of 30 amperes. That's the situation in the beginning. It's a copper wire. And the first question you're being asked, what is the electric field inside the wire itself? Let us take a random section of length L. Then the resistance R of length L equals rho times L divided by the cross-sectional area, which would then be, if you accept my R0, it would be pi R0 squared. What is the voltage, the potential difference, if I go from here to here? That is the integral of E dot dl, so that would be E times L, because I have chosen a distance L. E and L are in the same direction. E is constant, the dot disappears, so I get EL. But according to Ohm's law, it is also the conduction current times the resistance over that distance L. And so what do I find? When I combine that, I find that the electric field inside is the conduction current times rho divided by the area, which is the pi r0 squared. And this, of course, is independent of little l. It better be independent of little l, because clearly Maxwell's equations doesn't give a damn, so to speak, about what you choose for L. It has to be independent of L. So here you see it, and if I put in the numbers, but don't take my numbers always too seriously, because I can easily make mistakes, I found sticking in the numbers 0.15 volts per meter. Now you're being asked, what is dEdt? Well, you will say there is no dEdt, because the current is a constant. But they are going to sneak on you that now they are going to increase the conduction current with a huge amount, 6,000 amperes per second. So what is now dEdt? Well, that's the derivative of this thing. So that is rho divided by the area times dic dt. And you know that is 6,000. If I stick in the numbers, I may well have made a mistake. I find 30 volts per meter per second. That would be my answer. That's right, that's the EDT. Now, if we were charging, or if we were discharging a capacitor, there would also be a second derivative of the EDT, of E versus time, I should say. Second derivative of the electric flux through the surface. That, however, is not the case now. And you may say, well, that's strange because the current is changing. Well, but you're not charging up a capacitor. You're not building up a charge on a plate, so you're not increasing the electric field. At least you're not. You are increasing the electric field, that's what you're doing, but you don't have a second derivative of the electric field. So if this were a capacitor, and you were charging a capacitor with a changing conduction current, then as you will see, you will get a d2 EDT square, but here you won't. So this one equals constant, even though you have a changing conduction current. Having recognized that, you now are being asked to calculate the displacement current. Well, the displacement current, again, they don't specify the surface. It's a pretty sloppy of the authors, but I will assume that they mean the total one. That means the displacement current going through the cross-section, the flat surface of the copper wire. So it's epsilon 0 It is the EDT times that area, which pi r0 squared. The dot product disappears because the area, the dA's and the e's are in the same direction. And so, you'll find now the EDT you calculated is 30 volts per meter per second. So you find a number. If I calculate the displacement current density, then I even lose my area. I get epsilon 0 times the EDT. And if I did not make a mistake, which I could easily have done, I find 2.65 times 10 to the minus 10 amperes per square meter. Now look at this number. This is an extremely small number. And the reason why the second term of Maxwell's equations is often, but not always, but is often very small, is because of this epsilon 0, right, which is this 8.8 times 10 to the minus 12. But there are cases where it is not negligible. You're being now asked to calculate the magnetic field B at a distance r from the wire, which is 5 centimeters, which is larger than r0. It doesn't have to be much larger, it happens to be larger than r0. So it's outside the surface. Well, here is that cross-section of the wire. My r, which is 5 centimeters, I choose obviously a circle, a concentric circle, and I have to attach now an open surface. Well, there is nothing to be accomplished by being fancy with hats and paper, shopping bag surfaces. I would now simply go for this surface. That's all there is to it. If I go for this surface, remember that only through this surface is there a changing electric flux. But keep in mind, if you go through the integral of B dot dr, so you get B times 2 pi r, that the first term of Maxwell's equations, the conduction current term, is not 0. Neither is the displacement current term. I put a mu 0 outside, and I will calculate the situation when t equals 0, when the current was 30 amperes. A little later, of course, the current is higher. But I'll choose it, I will calculate at this moment. So I get a 30 here. That's mu 0 times IC at time t equals 0. So this is t equals 0. Now I have to add epsilon 0 times the EDT times the area. But it's this area, not this area. Because there is no changing electric flux going through this area. So I have now times the area, which I will call pi r0 squared, which was, I believe, this 4 times 10 to the minus 6 square meters. Well, earlier we calculated this, which was ridiculously small, and when you multiply these two, you get an absurd number, which is something like 10 to the, of the order of 10 to the minus 15. And so you see that in this case, even though the current is changing with an absurd amount of 6,000 amperes per second, the magnetic field at this location r, 5 centimeters, is exclusively dictated by the conduction current. And so to a high degree of approximation, you still get that it is I of C divided by 2 pi r. And if I calculated that correctly, I found 1.20 times 10 to the minus 4 Tesla. That's what I found. And this is then at t equals 0.